Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name's Sean Perry. These are guided notes number 15 in the series on section 3.3, Linear Systems by Substitution and Elimination. The first thing we want to recall is, what do we mean by an ordered pair is a solution to a system of equations? So when we talk about a system of equations, specifically in this case, a system of linear equations, we're going to be talking about a set of several equations sort of held together by this brace symbol. And we have some repeated x's and y's for our variables in each one. Now, this particular xy pair needs to satisfy both the first and second equation. So for example, if I plug in x and y to the first equation, I'll get -9, which is what it prescribes. And likewise, if I plug in 5 and 2 into these x and y's, I also get -28 when I evaluate. And that means this is a solution to the system. It is a single xy pair that satisfies or makes true both equations. On the other hand, if we look at something like problem 2, we can see that it isn't going to be a solution. 3 minus 4 might satisfy the first equation, but it doesn't satisfy the second equation. And that's because if you plug in 3 and you plug in -4 and evaluate, you wind up with 17, 9 plus 8. You don't wind up with 19, and so this doesn't actually satisfy the second equation. So that's fine. That just means that this isn't a solution to the system. Now, linear equations in general, we'll talk about lines or planes or the higher dimensional analogs of these things. But in any case, we're only going to have, for linear systems of equations, the following three options. You can have one solution, no solutions, or an infinite number of solutions. That's it. You can't have, for example, two solutions. Now, the most easily visualized situation is when we're talking about a system of two equations with two unknowns, because then we're just talking about lines, and there's only these three things that two lines can do. They can either intersect at one spot, they can be parallel, or they can actually be the same line, corresponding to one, none, or infinitely many solutions, respectively. The situation when we start to talk about planes is going to be a little bit more difficult, because the intersection of two planes is going to perhaps be a whole line's worth of points that will be common to two planes. And there might be situations where we could have parallel planes, and then these three planes don't actually have a common intersection anywhere. Or we might have the situation where we do have an intersection of three generic planes, and these guys will form some kind of mutual intersection where we now could say that a single XYZ point is common to all three planes. This is occasionally a more tricky thing to visualize, but there are still only these three solutions of one, none, or infinitely many. A bit of terminology: a system of equations that has at least one solution is called consistent. If it has no solutions, it is called inconsistent as such. The meaning of dependent and independent are a little harder to parse out. Suffice it to say, a system is dependent if an equation can be written as the sum of the other equations times by constants. For parallel lines, it is dependent if they are in fact the same line. In solving a system of equations by graphing, you simply graph the lines and look for their intersection, which is here at point B. For number 6, we're asked to look at the graph of this system of equations, and here we can see the intersection between the two lines is our point. It looks like, judging by the tick marks, this might be at -3, 3, but how could we check that? Well, we could plug that in for x and y and find out that it does indeed satisfy both of the original equations. And thus, -3, 3 is indeed a solution to this system. Here's one where they ask us to solve it by graphing. This works sometimes if the graphs are particularly nice. And in this case, if we graph the first one in yellow, the second one in orange, we can see that they do have this very clear common point of intersection at 2 minus 3. We could check this by plugging it in for x and y if we like. Problem 8 asks us to solve the system of equations with the substitution method. So in the substitution method, we solve for one of the variables, which is in fact already done for the second equation. And then we want to take advantage of the fact that at their point of intersection, these two y's should have the same value. So we can plug into equation 1 where we see the rules that we have for equation 2. So notice I've replaced that y with the rules for the y in equation 2. Then we can proceed to just solve this as an equation in one variable. This gets us 9, and plugging back 9 in for x, we can find out y. So our xy pair is going to be 9 minus 3. Likewise for this one, I'm not quite solved yet for one of the variables, so I begin by solving for x. If x is equal to negative 2y minus 12, then in the second equation where I see such an x, I can replace that with negative 2y minus 12. Distributing, grouping like terms, and solving, we have y is minus 3. And plugging that back into our equation for x, in terms of y, we then get x is negative 6. So we have a solution at negative 6, negative 3. Likewise for this one, well, they're both solved for y, so substituting one into the other means setting them equal to each other. If I do this, I can clear denominators by multiplying on both sides by 4, and now it's just a simple linear equation, so we group like terms, divide off our coefficient, and we get 16 for x. Plugging that back into either equation, we'll get 4 for y, which gives us our ordered pair of the solution. For number 11, they ask us to solve by the elimination method. The method here is to make it so that one of the coefficients is the negative of the corresponding coefficient in the other equation. So notice right here we have a single y, and corresponding to that there's a 5y in the second equation. If I multiply the first equation on both sides by negative 5, this is still a valid line. In fact, it's the same line that we started with. We're just going to have different numbers. But now, adding on both sides, I can sum these two equations together. Now that's legit, because since these two sides are equal to each other, by adding one to the other, I'm really doing the same thing on both sides. And something good happens when we have the equations lined up like this so that one coefficient is the negative of the other. Their sum is 0, and we have eliminated y. Now for x, we have a negative 31 for a coefficient, and that's going to be equal to 62. Dividing that off, we have x is negative 2, and then substituting that back in for x, we can solve for y to get minus 7. So we have a solution to the equations at negative 2, negative 7. To solve the next one with elimination, we want to take the first equation and multiply it by 4. That will make it so that the two x's are negative and equal of each other and equal in magnitude. We could have also multiplied this by negative 2 to make the y's cancel. But in this case, the x's will cancel. When I add the two sides together, we'll get 18y is equal to 18, which tells us y is 1. Subbing that back into either one of the equations, we can solve for x to give us 1 as well. So we have a solution at 1, 1. Here we have an equation that we can still solve by elimination, but there's no single multiplication of numbers that's going to do it for us. No whole number multiplication anyway. The easiest thing I think to do here is simply manipulate both equations. If I multiply this one by 3 and this one by minus 4, I'll wind up making the y's opposite from one another. Then when I take the sum, I'll wind up with 5x equal to negative 5, which tells me x is negative 1, and substituting back into one of the equations and solving for y, we get minus 5. Now, these other equations show us what can go wrong. We should note here that, first of all, this is out of order. If I rearrange things, it's a little bit more easily seen that one equation is just the constant multiple of another, which tells us they are dependent and in fact parallel and overlapping. So, but if we tried to solve with elimination, say, I might times the first one by 2 and rearranging and stacking appropriately, we add both sides together to get 0 equals 0. Now that is always true. That's a tautology. That's not a contradiction. 0 is of course equal to 0. It happens no matter what x and y are. And so actually we have an infinite number of solutions. Anything which satisfies either of these equations will be fine. One, if it satisfies one, it satisfies the other. They're just constant multiples of each other. In particular, I've solved for y here. Anything on this line, any point on this line would be a solution to both equations, and there are of course an infinite number of points on a line. Now with this one on the other hand, we have the x's and y's are sort of constant multiples of each other, and we can see that if we try to do elimination by multiplying the top equation by 2, when we sum them we get 0, with no variables at all left over on the left-hand side. But on the right side, I get minus 6. Now, 0 is not equal to minus 6. We have a contradiction here. And so there is actually no solution. The assumption that was false, that we assumed in order to get this contradiction, was that there was a common solution to x and y, that this x and y could possibly be the same as this x and y. But it turns out that's not true. There is no intersection between these two. These are lines which are parallel, but not dependent. So we wind up with no solution in that case. The same thing happens in this one. Let's rearrange things a little bit, and then multiplying by a constant, we can see that we actually have complete cancellation of both variables on the left-hand side, but incomplete cancellation to just a 2 on the right-hand side. 0 is not equal to 2, and so this is an inconsistent equation with no solution. Let's look at some word problems. If I have two numbers that add to be minus 6 and have a difference of minus 4, I can write down two equations that describe those facts this way. This is ripe for doing some elimination. If I add these two together, the b's cancel and I get 2a is equal to minus 10, which tells me that a is minus 5. And then plugging this back into either equation, I could get minus 5 plus b is minus 6, for example, which tells me b is negative 1. For the next one, we're also given two facts. One, that a man has a total of 24 coins, and the other that he has 315 cents, made entirely of dimes and quarters. So let's let D be the number of dimes and Q be the number of quarters. Then these two must sum to be 24. But 10 is the number of cents in a dime, and 25 is the number of cents in a quarter. So the total number of cents that he has must be given by the second equation. We can use elimination to solve this by multiplying the first equation by 10 and summing. This gives us that Q must be equal to 5. Then plugging that back into our equation for dimes, we find out that the number of dimes must be 19. Another common type of word problem that uses these systems of equations is to say that we had a certain number of people admitted to a theme park and that different amounts of dollars were charged for each ticket, and they give us the total number of dollars. So the total number of people was 253, that's children plus adults, and the total number of dollars of revenue earned was 642, which is the price of a children's ticket times the number of children plus the price of an adult's ticket times the number of adults. And this is going to give me 642. So what we could do is solve this for the number of adults by minusing the number of children over to the other side, substituting that in for A, distributing my 4, and then grouping like terms and solving, we wind up with C is equal to 148. Plugging that back into the equation for the number of adults, we get the number of adults is 105. Here we have a straightforward question involving savings. So a man is putting his money into a simple interest account. This is going to give him interest equal to a percentage times the amount of money in the account. They say that the amount of interest that he gained was $8,162 after investing some money in a 6% account and some money in a 10% account. But since this 10% account is more risky, he puts twice as much money in the lower interest account. So 2 times the number of dollars in the high risk account is equal to the number in the low risk account of 6%. So that gives us an equation, 2y equals x, that solve for x. Already we could just substitute that in where I see an x, and now we only have an equation of one variable. Distributing, combining like terms and solving, we have y is equal to 37,100, and plugging that back into our equation for x here, we have x is equal to 74,200. So I'd like to talk now about a 3x3 system of equations. We have a linear system. The way we can tell it's linear is the only thing that we're doing is adding and subtracting variables from each other, possibly times constants. Those are the two things you're allowed to do in a linear system. No squares, no division, no roots, nothing like that. Just multiplying by constants and adding things together. Now, we're going to look at two ways to do this problem. One, using a graphing calculator or, technology, using matrices, and the other using, elimination, substitution, that kind of thing. I'll go into more detail as to the matrix process in the next video, but for right now, I'd like to show you at least once how to do such a thing by substitution. We might take equation 1 and solve it for x. The coefficient is only 1 for x, so that can be pretty easily done. Then if I substitute that equation into equation 2, replacing my x with this expression, and simplifying, we get the following. Finally, if I substitute equation 1 into equation 3, we could distribute group-like terms, and get the following. And this gives me two equations made from equations 4 and 5 here. These only have two variables and two equations, y and z. And so now we're sort of free to reset the world and solve this however we see fit. We could do substitution, but one y is a multiple of the other, so we might as well multiply by 4 and get these off by a sign, sum them together by Gaussian elimination to give me the equation 75z is equal to negative 300. This can be solved for z to give me negative 4. Reversing our substitution, we plug that back in for z and solve for y to get z as 2. And then we take our original equation and substitute both of those back in to find out that x is equal to 0. And so we have a solution at x, y, z is equal to 0 to minus 4. However, by far faster is the technological approach. We're going to plug these things into a matrix, but we need to know how to do that. I'm going to copy these equations over here, and we're going to take these 12 numbers and put them into a matrix in this way. So notice I'm just taking the coefficients and putting them into this 3 by 3 matrix. And what they're equal to, I am putting into this far column, the fourth column here of this matrix. So as we discussed in the matrix videos, you want to go to Matrix, edit a matrix, put this in as a 3 by 4 matrix, and then put the following numbers in. Making sure our entries are correct, we quit back out to the main screen, and now we're going to go to second matrix, over to math, and up to this command called RREF. We'll talk a lot more in the next video about what this command is doing and how, but for right now we should just see how we can use it to solve systems of equations. When I plug this in, notice we have our x, y, and z answers here. What we've done is put things in reduced row echelon form. Reduced row echelon form refers to a special kind of n by n plus 1 matrix, where we have the identity matrix in this position and then a column matrix of values. And if we consider what that would be like in terms of a system of equations, it would say 1x plus 0y plus 0z is equal to, for example, 0 here. Or 0x's plus 1y plus no z's was equal to 2. And 0x's plus 0y's plus 1z is equal to minus 4. That's our matrix here. So we want to see that this is really just x equals 0, y equals 2, and z equals minus 4. Because from our reduced row echelon form, we can just immediately read off our answers 0, 2, and minus 4. So I encourage you to consider how to solve these equations by substitution, but all in all, I find it to be a very taxing kind of exercise that's just testing your arithmetic. And if you'd like to do that as a challenge for yourself, please be my guest. I also completely endorse using the calculator to do this kind of work. That's what it's for. What's interesting are the kinds of problems that we can solve using this methodology. So now let's talk about this particular one. We have an unknown price for apricots, apples, and starfruit. We know how many we bought of each, and we know how much the total cost was. Using this information, we can solve for the price of each fruit. What we're going to want to do is say that the total price, of course, for the number of apricots here was going to be 13 times its price. Same thing for 12 apples and 6 starfruit, and this would give me a total cost of 53.10. So writing down this system of equations, then encoding it into a matrix, which we could do by editing our old matrix and writing in these values anew. We check our data entry and correct any mistakes. Here I've accidentally typed too many starfruit, but that's because I accidentally wrote a 32 here. This should, of course, just be 3 starfruit. I don't care how much you like carambolas, 32 is too many starfruit. So once we have these values loaded, we can fire off the exact same command again to put this in reduced row echelon form. And this will give us the prices of $1.50, $1.70, and $2.20 for my apricots, apples, and starfruit respectively. We can then take that output and encode it into our answer as follows, and that would be that. I think 23 is actually a really cool problem because you might know that 2 points determine a line being a degree 1 polynomial. But did you know that 3 points 3 distinct points, which are not collinear, will determine a particular parabola, which is a degree 2 polynomial. And in general, if we have n points, not all on a degree n minus 2 polynomial, then these will determine a degree n minus 1 polynomial. And the formalism for figuring out what the coefficients of that polynomial should be is precisely solving this system of equations. So for example, if I know that we have y given by ax squared plus bx plus c, then I can write down these 3 points in the following way. Replacing x with the x values, I get this particular y value. So notice, even though a quadratic equation isn't a linear equation, it is linear in its coefficients. Treating the coefficients as the variables and the x as something we know, we do get a system of linear equations. And so we can take that system of linear equations and encode the coefficients, which are actually the values of x that you get plugging that into x squared, x, and here's our constant term. So we encode this system into this matrix, we fire off reduced row echelon form, and that would give us the following values. Now, I just wanted to notice one thing, which is how to go from the decimals to the values. Let's really quickly put our matrix in here as matrix A. My apologies, my usual emulator is not working today. Still trying to figure that out. But we can put those values into our matrix, quit, and put it in reduced row echelon form. Now, this gives us some decimals, but fortunately, on all TIs, there's a button for that. We store as fraction, and it'll give us our values nicely. So there we have it. This is the particular polynomial that goes through those particular points. And so we could find any degree polynomial we wanted if we just knew n plus 1 points, where n is the degree. Okay, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.